So cylindrical coordinates are really useful in problems that involve symmetry about a particular axis. Now, some of you are going to discover on at least one of the homework problems at a later date. I forget which section or where, but you don't have to have symmetry around the z-axis. You could actually have a slightly different version of cylindrical coordinates if you're working around the x-axis or the y-axis. But the way that I've set up cylindrical coordinates, I'm assuming that I have symmetry about the z-axis. And I'll leave it to you as a little challenge to figure out how would you do polar if you wanted to say make x, let's say r cosine theta, z r sine theta, and then y y. When would that be useful? What symmetry would you want there? So if you want to think about that, you can, particularly with things being online, but even in general, we typically focus on symmetry around the z-axis for using cylindrical coordinates. So let's take a moment and just see how we can simplify surfaces. So the surface, z equals x squared plus y squared, I hope we're all immediately can see in our minds what this looks like, right? This is a paraboloid opening up. Well, if you want to write down the equation in cylindrical coordinates, this becomes z equals r squared. And that's somehow much easier to work with, to integrate, so on and so forth. So we're going to use cylindrical coordinates to do triple integrals. And so I think we'll scroll down and see how it goes. So because we're assuming symmetry about a certain axis, that's typically when you want to pull out cylindrical, we're going to focus in our setup over type 1 solids. And remember, a type 1 solid it's a solid, maybe let's just, for example, use something like this, okay? Maybe it's a solid where you've got, when you make your first cut, you make it vertical along the z-axis, parallel to the z-axis, and you're going from a z equals to a z equals surface. And so that's the kind of situations that we typically are going to use cylindrical coordinates. So I don't actually want to work over that nice ice cream cone. It makes me hungry, and that would be bad for me to have ice cream at this time of day. Let's just think of a generic type 1 solid. So the triple integral in Cartesian coordinates, how do you switch it to cylindrical? Well, first off, notice that instead of dz, dx, dy, or whatever, there's 6 ways you could order the dv, we're going to write this dz, dr, d theta. That's typically going to be the order that we always do it, dz, dr, d theta. And then just like in polar, when you make the switch, an extra r is kicked out. And I would love to show you where that comes from, but we just don't have time. I sometimes can cover that in class. There's a Jacobian, you can Google it, it's kind of interesting. Anyway, you just pop the r right there. So there's your r, dr, d theta, just like before. And then whatever your function was, you just switch the x's and the y's to polar. So x is now r cosine theta, y is r sine theta, and z just stays z. And then your surface, your solid that you're integrating over, if you remember, it was type 1, so you can actually convert z equals whatever the surface was, the bottom surface, to some function of r, x and y, which becomes a function of r cosine theta, r sine theta. It becomes a function of r and theta. And so, by the way, this is your bottom z equals, I said z1, I just mean z equals u1 of that. And then up here, we're going to go to the top surface, which is going to be, it was z equals u2 of x and y. Now it's going to be u2 of x is r cosine theta, y is r sine theta. And oops, my theta's got a little smudged, but you can see that. I don't usually write the z, but I will, at least temporarily. The next part, you're just switching to polar, so this is going to be some h1 of theta to h2 of theta, and then your last bounds are always going to be constant. So you can write this down, but really this is best learned by example. So let's, I've got that jotted down for reference, but let's actually practice this via example. So I think I'll stop this video here, and then